Hi everyone and welcome. In today's video we are going to explore a result that follows very nicely from the axiom of completeness which we covered in the previous video. This new result is called the nested interval property. We will first go through the proof of this theorem and then we will look at some examples. So the nested interval property states the following. Let's suppose that for each natural number we're given a closed interval I sub n. So I1, I2, I3 and so on. And a closed interval from an to bn is just the set of all real numbers x that are between an and bn, including the endpoints an and bn. So notice a closed interval defined in this way can actually never be empty. At the very least, if the endpoints happen to be the same, then we will just have a singleton. Otherwise, they're infinite sets. So now continuing with the statement, let's also assume that each interval contains the next one. So in contains in plus 1. Then the resulting nested sequence of closed intervals has a non-empty intersection. So what we have here is actually infinitely many closed intervals, and as we move along this chain, the next one is contained within the previous one. So I1 is where we start, it's like the largest interval, and then when we get to I2, it might be possibly a little bit smaller, but it's going to be contained in I1. And then as we get to I3, it might be possibly a little bit smaller, but it will be contained in I2 and hence contained in I1 and so on. And the claim is that if we were to take the infinite intersection of all these closed intervals, well then the intersection will be non-empty. And by non-empty, we mean that it could maybe just have a single element, or it could have infinitely many elements, but it will never be empty. And we will see this more clearly with examples later on. But as a visual diagram, let's say the first interval I1 is from A1 to B1. Then the next interval I2 must be within the first interval, so it could be possibly a little bit smaller. So here's I2, it's from A2 to B2. And then I3 must be contained within both of these. So here is possibly I3, it's between A3 and B3. And we keep going in this fashion forever. And the claim is that there will always be a number, or possibly infinitely many numbers, that are contained within all of these intervals. Now let's get started with the proof. What we would like to show is that there is at least one real number that lies in every interval. And so in order to do this, we would first need a candidate for such a real number. I would like you to consider the set of all left endpoints. So here I have defined the set A, which is the set of all left endpoints. And if you were to look at the visual diagram here, what I'm doing is I'm just collecting A1, A2, A3, and so on forever. Our set A comprises of all these left endpoints. Now there's two things to note about this set A. The first is that this set A is non-empty because, for example, A1 is in A, which is the left endpoint of the first interval I1. And moreover, all of the B's are an upper bound for A. So if you look at this diagram, all of the B's here, the right endpoints, happen to be upper bounds for A, and this is because the intervals are nested. Since the intervals are nested, the B's will always be to the right of all the A's. And so therefore, since A is a non-empty set of real numbers, which happens to be bounded above, the axiom of completeness tells us that A must have a least upper bound. And so we can call X to be the least upper bound, or the supremum of A. And going back to this diagram, what we're basically doing is we have the collection A of all left endpoints, A1, A2, A3, and so on forever, and the supremum of A, which we called X, would lie somewhere over here because the supremum is an upper bound for A. And so therefore, it's going to be greater than or equal to all the A's. And so this is a reasonable candidate for something that could be in all of these sets. And indeed, our goal will be to show that this element X actually does indeed lie in all of the intervals. That is, X is an element of In for all natural numbers n. To do this, let n be an arbitrary natural number, and then let's consider the nth interval In. Well then, An belongs in A because A is the collection of all left endpoints and An is the left endpoint of the nth interval. And moreover, we have that X is the supremum of A. And one of the properties of the supremum is that it is an upper bound of A. And so therefore, X must be greater than or equal to An. Next, as we discussed, all the B's are upper bounds on our set A. And so in particular, this Bn, which is the right endpoint of the nth interval, this should also be an upper bound for A. But we know X is the supremum of A, and the other property of the supremum that it is the least upper bound of A. And so what we get is that X must be less than or equal to Bn, because Bn is an upper bound for A, whereas x is the least upper bound for a. Overall, we get that x is between an and bn. In other words, x lies in the closed interval from an to bn, which is exactly the nth interval. But n was an arbitrary natural number, and therefore x is actually an element of in for every natural number n. Well, if x lies in every single interval I1, I2, I3, and so on, well, that means that x lies in their infinite intersection. And therefore, we conclude that the intersection of all the closed intervals is actually non-empty, because we just constructed an element inside this intersection. And this completes the proof of the nested interval property. Next, I would like to mention some important remarks. The first is related to the axiom of completeness. If you recall from the previous video in which we covered the axiom of completeness, I mentioned that there are other mathematical statements that also express the completeness of the real number line. And it turns out the nested interval property also captures the completeness of the real number line. It also expresses, in another form, the idea that the set of real numbers has no gaps. However, it is slightly weaker and needs an additional assumption, which is called the Archimedean property, that we will cover in the next video. But with this additional assumption, it actually does become logically equivalent to the axiom of completeness. And the second point I would like to mention is that the intervals in the nested interval property must be closed for the conclusion of the theorem to hold. If they're open, then the intersection may or may not be empty. As an example, let's consider the following sequence of open intervals in, which is equal to 0, 1 over n for all natural numbers n. So the first interval would be the open interval from 0 to 1. The next interval I2 would be the open interval from 0 and a half. I3 would be the open interval from 0 to a third. And so what we see is that these intervals are getting smaller and smaller and smaller, shrinking to 0, and moreover they do not include 0. And so therefore the intersection of all these intervals will actually be empty. And you could actually formally prove this as well. Let's suppose for contradiction that there was some real number that was in all of these intervals. So what that means is that this is a real number x that is greater than 0 and less than 1 over n for all natural numbers n. However, as x is a positive number, you can find actually a natural number big enough so that 1 over n naught is strictly smaller than x. Now, we will actually look at this property in the next video. It's something called the Archimedean property. But the point is that x cannot be less than 1 over n for all natural numbers if x is positive. We can actually find a number in between 0 and x. And so this contradicts the fact that x is actually less than 1 over n for all natural numbers n, and therefore such an x cannot exist. Another way to look at it is that the n naught interval will actually end up excluding x, and so therefore x cannot be part of the infinite intersection. It does not lie in all of the intervals. At some point, this x will actually get excluded by these intervals up here, and so therefore the intersection of all these open intervals is actually empty. In the second example, let's once again consider a sequence of open intervals, but this time the open intervals are of the form 0, 1 plus 1 over n. And you can try to plot some intervals. You can see that the first interval would be the open interval from 0 to 2, and then we would start shrinking towards 1. But we will actually never exclude 1. We will always be to the right of 1. This will end up reducing to the interval 0, 1, excluding 0 by including 1. And so in this case, we see that the intersection of all these open intervals is actually non-empty. In this case, there's actually infinitely many elements in their intersection. And that brings us to the end of today's video, in which we cover the nested interval property. In the next video, we will explore the Archimedean property, which helps us understand how the set of natural numbers fit inside the set of real numbers. Thanks for watching. If you enjoyed this video or found it helpful, I would really appreciate it if you could like the video and subscribe for more content. And if you have any questions or thoughts, feel free to leave a comment down below. I would love to hear from you.